Alright, so today what we're going to look at is we're going to look at some new rules, like basically what are we going to do when we have a product or a quotient, and how are we going to take the derivatives of those. What we have seen so far, just kind of as a review, we've seen the derivative of a power function where you simply multiply the power times the coefficient and subtract 1 from the power, so there's our power rule. We've learned the derivative of the sum and difference. The derivative of a sum or difference of functions is the sum or difference of the derivatives. So we can kind of think of it like distributing the derivative through, which unfortunately does not work for product or quotient. We have the differentiation rule for a constant. If I want to take the derivative of a constant, it's going to equal 0. The derivative of a constant times a function, you can pull the constant out and multiply the constant times the derivative of the function. We learned some basic ones for some of the transcendental functions. The derivative of sine is cosine, derivative of cosine is negative sine, and the derivative of e to the x is itself e to the x. So these are all rules that you should already have in your flashcards that you're basically memorizing so that you have them in your tool belt when we're doing the application problems, which is kind of the point of the calculus. You do want to remember that the function f of x is your y value generating machine. That anytime you need a point, so if I want to find a point, if I have an x value of c, I plug the c value into the function to get its y value. So this is your point generator. Go back to the original function. If I am looking at the derivative is your slope value generating machine. Whenever you need a slope at a point, an instantaneous rate of change, you are going to use your derivative. So m equals f prime of c is your slope of a tangent at x equal to c. Or we also know that it is the instantaneous rate of change or instantaneous velocity at x equal to c. Okay, so we want to make sure that we keep that in mind. So what we want to do now is we want to kind of come through and we're going to start talking about the product rule. So what we're looking at here is we're trying to come up with a rule for the derivative of when I have one function, f of x, times another function, g of x. And we want to take that derivative with respect to x. So again, we're going to do all of our proofs by going back to our limit definition. So I'm going to use the limit as h goes to 0 of my plug in x plus h. So we would have f of x plus h times g of x plus h. So there's your function where you plug in the x plus h minus the function that you're taking the derivative of. So f of x, g of x, all over h. So that's what we're going to use to kind of develop a shortcut rule. Now, in math, and this is kind of a trick that we like to use in multiple situations and in multiple proofs, what we basically can do in a proof is, because I don't really want to change this expression that I have, but I would like it in a slightly different form. And so really the only legal things you're allowed to do is I could multiply by a form of 1, or I could add a form of 0, okay? And now we're going to be kind of smart about this, and I wouldn't expect you to come up with this, but what we're going to do is we're going to add a nice form of 0. I'm going to put this in red so that we can highlight it. So what I'm going to add is f of x times g of x plus h. Actually, I'm going to subtract this, and then I'm going to add it. And the idea here is by simply inserting this in the middle, that my net gain here, that all I have simply done is add 0. And so by adding 0 here, I haven't changed the expression at all. All I've done is given myself a little bit more to work with, and somebody really smart and intelligent came up with what form of 0 that they were going to add in. But you'll see why in a second why I've done this. So what I'm going to do now is I'm going to group these and I'm going to split this fraction. I'm going to take these first two and group them together, because we also know that the limit, if I can get the limit of a sum, I can distribute the limit across the sum. So I'm going to conveniently rearrange this with the first two terms together. and put that all over its denominator, common denominator h, and then I'm going to add to that and then do the last two terms together. So what adding that 0 does is it allows me to kind of play with the expression that I have, to put it in a somewhat nicer form. And so what you'll see here is, in taking a look at it, is both of these terms now have a common factor. So there's a g of x plus h here and here in both terms of the numerator, so I am going to factor that out. And likewise over here, the common factor that I have is f of x. So I'm going to pull the f of x out of the second term. Okay, so we're basically just doing a little algebra. Let me change color here so that you can see it. So now we take a look at it. I'm going to have the limit as h goes to 0. I'm going to go ahead and distribute the limit over this while I'm factoring, because it's the limit of a sum is the sum of the limits. So I'm going to factor at the same time. We're far along here that we can do two things at once. And so what I'm going to pull out, once I pull that g of x out, now I'm going to have f of x plus h minus f of x all over h. And hopefully you'll start to be like, oh, hey, wait a minute, that looks familiar to me. I'm going to do the same thing over here. I'm going to pull out the f of x. What I have left is g of x plus h minus g of x all over h. And so you can start to see, hopefully, why I chose that convenient form of 0. The limit of a product is the product of the limits. So we can take the limit as h goes to 0 of g of x plus h times the limit as h goes to 0 of this difference quotient, which hopefully right now you're saying, hey, wait a minute, that's nothing more than a derivative rule. Do the same thing here. The limit as h goes to 0 of f of x, the limit as h goes to 0 of g of x plus h minus g of x all over h. And again, hopefully you're noticing that I basically have derivatives here. So this is nothing more than f prime of x, and this right here is nothing more than the definition for g prime of x. So basically what I have left to do in this problem is to figure out the limit as h goes to 0 of g of x plus h, which basically I can just plug in 0. So I'm going to get g of x for the first limit times the f prime of x for the second one, plus, now since there's no h in here, you can pretty much think of this like a constant, and the limit of a constant is the constant, so that would give me f of x, and again times g prime of x. So what we've basically shown in this proof is that the derivative of the product of f of x times g of x is way more complicated than actually distributing the derivative through, which is what you're going to be tempted to do. But you are not going to do that because we've gone through our steps here and we've seen that what we have to do is take the second function times the derivative of the first, and then plus the first function times the derivative of the second. So this is going to be the rule that you're going to put on your flashcard that you are basically going to memorize, because I obviously don't want to go through the limit definition and come up with that fancy form of 1 each time that we look at this. A lot of times we will shortcut this, and I'll write it as simply f times g, so that way I don't have to worry so much about doing it, and I would do g f prime plus f g prime. And so that's going to be the rule that you're going to work on and memorize. Now let's kind of go to the next page. A couple of things I want you to do. The incorrect product rule is to distribute, okay? If this happens anywhere, I'm going to tell you that you will get no credit on the AP. If there is a problem that has a product rule involved in it, and you simply distribute and take the derivative of each piece, you will get no credit. So you want to make sure that you never do this, that you remember that the product rule is super special, that you're going to memorize, and that you cannot distribute a derivative over a product. Now that's different. When we were doing the limit of a product, we could certainly take the limit of f times the limit of g, provided the limits existed. but we cannot do that with derivatives, and so that's a little different, and we want to make sure that we pay attention to that. All right, so our correct product rule, here we are again, and notice arithmetic is commutative, so you can write this as g of x times f prime of x plus f of x times g prime of x, or you can do it the other way. It's not going to matter because I'm adding, so it doesn't really matter which one I have first. When we get to the quotient rule, that of course is going to be a little different because we're not going to be adding. You'll see that shortly. So we want to make sure you get this memorized, whichever version you want to do. Let's do a couple of examples here to kind of show how it works. So prior to product rule, so before product rule, what I would have done here is I would have multiplied out. I would have done the work, and I would have done the FOILing and multiplied this out, and then I would have had the sum or difference of power rule, and then I could simply go ahead and take the derivative. What we're going to do here is we're going to do this two different ways, just to kind of show you. We're going to use the product rule first for A, then we're going to sledgehammer, that's the multiplying it out down here, the old way, and then we're going to show graphically using nderive and kind of show just to practice that as well, right? So let's do A first. So A, we're going to do product rule. So product rule says, and if I want, we can slide up here since we have it in. You take the second one times the derivative of the first. So the derivative of that would be 3 minus 4x. And then we have plus, and then we have the first one, 3x minus 2x squared, times the derivative of the second. The derivative of a constant is 0. Derivative of 5x is 5. So that gives us our derivative. And if you are not using it for anything else, you would stop at this point and say, I found it. That's the derivative. Okay. Now, usually what you're going to have is you're going to have to simplify this. So I'm going to put this in a different color just to show you that you don't necessarily need to in this problem, but I want to verify to you that you're going to get the same thing, the same result in the end. So what I'm going to do here is I'm going to go ahead and I'm going to factor, or I'm going to distribute this out, I'm going to sledgehammer it. And you'll see why in a second, just kind of verify the two derivatives are the same. So this would be my 12 plus a 15x, and then we have our minus 16x, and our minus 20x squared, and then distribute through here as well, plus 15x minus 10x squared. So we do a little sledgehammer there. And then we simplify, we collect our like terms. I would end up with minus 30x squared. And then I have 30 minus 16, so plus 14x plus 12. And so when we take a look at that, that's going to give us kind of a simplified version of what that derivative is. And again, I do want to stress, you do not have to do that unless you are going to be using it and doing more things with it. They just ask you to find it, you kind of get here and stop here. Okay? Now, we're going to do it the other way, which is I'm going to multiply that out. So I'm going to do a little work in the beginning. So I'm going to take g of x and I'm going to FOIL. So that's going to give me 12x, and then minus 10x cubed. And then I have minus 8x squared, and then the outer terms would give me plus 15x squared. Combine your like terms, and let's put it in descending order. So minus 10x cubed, and then we have minus 8 plus 15, which would give me plus 7x squared, and then our plus 12x. And then you can see very quickly that if I were to then take the derivative at this point, the derivative using the power rule would be negative 30x squared plus 7, plus multiply 14x plus 12. So we get the same thing no matter what we do. Now, in this problem, you actually can do it either way. It doesn't really matter. However, there will be times where the product rule is simply going to be faster, and so we will use the product rule. And then just to kind of recap our nderive, let's show nderive, and I'm going to graph this just to verify that we have the same thing. Again, just to remind you how to do nderive on your calculator. So we're going to come over here and let's put our function into our y equals. So I'm going to clear this, and I'm actually just going to do it because I'm only really interested in the derivative. So I'm going to go straight to math and 8 and choose the derive. And I have it in the nice pretty print format. So I'm going to go ahead and put in my derivative with respect to x. And I'm just going to not even worry about multiplying it out. Just do your parentheses. 3x minus 2x squared. Close your parentheses. Do another set of parentheses. 4 plus 5x. And remember that when you want to graph it, we do x equal to x, because we want to do it for all of them, not just for one of them. And then we're going to graph. I'm going to go ahead and do it in the version before I simplify. We're going to be verified that it's the same, but we might as well just show 4 plus 5x times my 3 minus 4x. And then we had our plus 3x minus 2x squared. And then our last one, which was basically times 5. Alright, so let's try to zoom 6, see what happens on our graph. I love how this is so slow now that we have color. And hopefully eventually this will be coming up. And if you can see that it's blue and red all at the same time because it's graphing them basically right on top of each other. So if I hit trace, whenever it finishes graphing, I could zoom out if I wanted to, but I'm not going to. I was just trying to verify that they were the same. If it would ever stop graphing. Alright, so hitting trace, you can see that I'm on the derivative. Let's bring myself down here. Or maybe let's just type in a number. 1 looks like a good number. So 1 is negative 4.00001 on the derivative. And then if I move myself up to the other graph and I hit 1 again, you can see that, oh, it's a little off. But remember, why is it just a little off? Because derive is estimating your derivative, whereas this was exact. Okay, but it's close enough. Yeah. So that kind of just verifies to us that we pretty much have the same graph as we're going. Okay, so now that we verified that it works for the previous example, let's just do some quick practice. When you're looking at this, you do want to make sure you kind of notice it doesn't really matter kind of how you group them, but you want to group them so that you have two functions, so that you can kind of identify this would be the f and then that would be the g. So if I want to find the derivative of y with respect to x, notice I don't really have any options of multiplying it out. I pretty much have to use the product rule. So I'm going to do the second cosine of x, g, times, and sometimes I like to put parentheses in to make sure I've got all my order of operations, the derivative of f, so that would be 15x squared, plus my f, 5x cubed, times the derivative of g, the derivative of cosine is negative sine of x. Now this last one is kind of why I like to put the parentheses in. Because when you're looking at this, and if you don't put these parentheses here and you put this negative sign of x, it's going to look like subtraction if you don't have the parentheses. So I want you to get into the habit of putting in the parentheses that we have there when you're working at it. A little bit later, one of the things that we're going to work on, because we're going to be using these derivatives, is one of the things that we like to factor derivatives whenever possible. So now that I have two terms, if I were to have a common factor, we typically look for a common factor to pull out, and I definitely have a 5 and an x squared. So I'm going to pull out the GCF of 5x squared, and then simplify what's left. I would have basically a 3 here times the cosine of x. And then over here, I'm going to have a minus, and I took out a 5, and I'm going to have x sine of x. And typically, that's what we want to do with our derivatives, because one of the more important questions is where we have horizontal tangents and things like that, which would be where it's equal to 0, which would mean that when it's factored, we can use zero product property. So that's kind of one of the reasons why, if we were going to simplify, we would look for common factors to pull out. All right, so let's take a look at this one. Now, what you want to notice here is that you really first have a difference when you're looking at it. And the derivative of a difference is the difference of the derivatives. You can distribute over that. So if we were going to start this process to take the derivative, this one is kind of difficult. So I'm just going to go ahead and say I'm going to take the derivative of 2x cosine of x with respect to x, and this is going to require a product rule, minus the derivative of 2 sine of x. The constant just comes along for the ride. Derivative of sine is cosine. So I went ahead and actually took the derivative of the second part. I left this for the next step because this is going to require the use of the product rule. And so when we look at that one to do the derivative, I'm going to call 2x my f, and that's going to leave cosine of x to be the g. So we're going to come through here now and go ahead and just put equals because I already labeled it the derivative. I'm going to do my g cosine of x, put your parentheses, times the derivative of f, so that would be times 2, plus your first function, 2x, times the derivative of the cosine. Derivative of cosine is negative sine of x. And again, be very careful and put in those parentheses so that you don't think that that is subtraction. And then maybe you want to make it look pretty if you were going to work with this. There's not really a common factor here, so, well, actually there's a 2 that we could pull out, but that's really, usually when we look for a common factor, we want it to have x's in it. The 2 is not going to matter. So I'm just going to leave it as, oh, wait a minute, and once I think about this, 2 cosine of x, and then minus 2x sine of x, minus 2 cosine of x. Oh, look, we actually have some cancellation there if we just take a look at it. So these two things will cancel out, and our final answer, most simplified version, is negative 2x sine of x. And then so now it's ready to use if we want to. The big important thing to remember is that multiplication and addition are commutative, so it's pretty difficult to mess this rule up. It doesn't really matter as long as you do a function times the derivative of the other one plus the function times the derivative of the other one, just reverse it. This one's pretty easy. But again, remember, never do the derivative of a product as the product of the derivatives. If you distribute, you will get 0 credit for that. On my test, on the AP test, on anything that you do, they even stop right there if you do not know that you're supposed to be using the product rule.